Good morning, grade 8s, and warm welcome to all of you to the WorksheetCloud grade 8 Natural Sciences lesson today. If you have a question during the lesson, please can you send an email with your question to grade8@worksheetcloud.com. I'm so proud of all of you that you have taken the time and the effort to log into these lessons and you in control of your learning, and I just want to tell you that you can do this. I know it seems so difficult and it seems like such a struggle and you're missing your friends and you're missing your teachers, but I just want to congratulate you. You're doing so well. So well done. We're proud of you. Keep it up. And I'm looking forward to having fun with you in today's lesson. I am Mrs. Ernston, the WorksheetCloud Grade 8 Natural Sciences teacher. Please will you remember to take notes as we discuss things in class today. It really is important that you keep a record of these lessons so when you get back to school you can show your teacher what you've been doing. And if you have any queries or any questions throughout today's lesson, if there's anything that you don't understand and you need me to clarify, or if you need help with anything, please will you email your questions and queries to grade8@worksheetcloud.com. We want to finalize what we're doing with the particle model of matter in this lesson. So just to recap, you're going to need to be able to use the particle model to explain phenomena linking the energy of particles to temperature and energy changes. How can materials be made to change their state? So how can things change from a solid to a liquid to a gas? How does the particle model of matter help us understand the changes of states in material, such as melting, evaporation, condensation, and freezing? I need you to be able to draw phase diagrams that relate pressure and temperature and the phase of a substance. We're not going to be dealing too much with pressure. We'll be having a look at that towards the end of matter and materials. And then I do need you to try and understand graphs which illustrate phase changes in a substance. Here's a little activity that we can engage in the start of today's lesson. So I have given you some scrambled words. So all the letters have been jumbled up. I want to see if you are able to unscramble the words and tell me what each of them mean. So if you can just press pause on the video now and spend about 2 minutes unscrambling these words. So well done if you managed to get them correct. So we have vapor, vigorous, energetic, transformation, condensation, and evaporation. So now that you've got your brain all engaged in the activity, let's get on with the lesson. So here is a think link activity. So I want us to go through each of these items and see if we can find what links them all together, or what is a general theme for this page. So if we had to give this page a title, what title would you give it? So here we have something that's known as dry ice. You often find that in vendors who are selling ice cream, they put this dry ice into the special ice cream coolers, and you can see the vapor coming off the dry ice. These are mothballs. Often we put them into our cupboards and into old bags, or when we are storing things away, and they kill little fish moths that can come and eat your clothes and linen and blankets and things like that. So those are naphthalene balls. I want you to look closely at this yummy picture of chocolate, a milkshake, and I want you to have a look at what's happening on the outside of the glass here. Here we have a beautiful snowflake. Here we have an ice skater skating on ice, so we can see the blade going through the ice on the ice rink. Here we have a pot of boiling water. I want you to look very carefully at the bubbles and how they're distributed in the water. Here we have a lovely icicle. You can see here's our icicle hanging, and here we get a droplet of water forming. So I want you to hang on to these pictures, and I want to see if through the lesson you are able to make links and see how they relate to the lesson. So look out for any of these terms and things, make a note, and at the end of the lesson, we'll pull the think link together and we'll see where in the lesson did we come across each of these pictures. So I've got a little fun experiment that I would like you to do today. So obviously it's with your parents' permission, and it is a good idea for you to have an adult around with you when you carry out this experiment. So I've said, please, can you have a parent help you with this activity? And if you've got some form of safety goggles, please will you put them on? So this does involve seeing whether or not you are able to create some magic using a balloon. So are you able to blow up a balloon without blowing into it? Now, there are several ways that we can do this. And I know if you go and have a look on the internet, there are lots of different experiments. But with this one, I'm wanting to link it up with the particle model of matter. So have a look around the house, and if you've got some party balloons, that will be great. You'll be able to do this activity. If not, don't worry, because I've got a video clip coming up that can show you the reaction. However, if you are able to do this, you need some party balloons. You need 2 teaspoons of just plain normal tap water, a microwave oven. If you don't have a microwave oven, a pot of water on the stove is enough, and that's where it's really important that I have your parents around you to help you with this. Oven gloves, because it can get a little bit hot. Safety goggles if you've got, and then a large bowl of ice cold water. So please ask your parents' permission before you go rummaging around in the kitchen. What I'd like you to do is pour water into the balloon. So pour the 2 teaspoons of water and squeeze out any air before tying the knot in the neck of the balloon. Okay, so make sure there's no more air left in the balloon. Then I want you to place the balloon in the microwave oven and heat it on full power. But please, you only need to do this for a few seconds. If you don't have a microwave, what you can do is you can place the balloon into a pot of water on the stove. You can make it cold water, put the stove on, and watch the balloon. As the water in the pot starts to heat up, watch what happens to the balloon. So what I would like you to do is I want you to observe what happens in this experiment. And if you are doing this experiment at home, I want you to remove the heated balloon with an oven glove. Shake it gently, and if you are very quiet, you might hear something happening inside the balloon. I want you to tell me what it sounds like. And then once you've done that, I want you to place the balloon in a bowl of cold water. So this little clip here is just showing you what happens when you put the balloon with 2 teaspoons of water and you've tied a knot in the neck of the balloon into the microwave. Okay, so that's why you must really be careful to not leave your balloon in the microwave for too long. And please remember that this was a slow motion video, so you'll just need a couple of seconds. We really don't want your balloon to burst in the microwave. So watching this clip, I want you to think about what did you observe happening in the microwave? And then what I need you to do is to remove the balloon from the microwave or the boiling pot on the stove before it bursts. Shake it gently, and I want to see if you can hear anything and what it sounds like. And then once you've done that, if you can place the balloon in a bowl of cold water and observe what happens. So, did the balloon have any air inside it at the start of the experiment? What made the balloon expand? What is the name of the gas that made the balloon expand? What did you hear inside the balloon when it started to cool down? What caused that sound? Where did the water droplets inside the balloon come from? What happened to the balloon when it was cooled down in the cold water? And which changes of state did the water undergo in this experiment? So you can pause the video now and you can try and answer each of these questions. I know it's going to take you a while, not a problem, I'll wait for you. So let's have a look at some of your answers. Did the balloon have any air inside of it at the start of the experiment? Well, no, it shouldn't have. The balloon shouldn't have had any air inside of it because you should have squeezed all the air out and tied a knot in the neck of the balloon before you started to heat it. So then what made the balloon expand? Well, the balloon expanded because the water, the liquid water inside it was evaporating. So the balloon was filling with vapor. What is the name of the gas that made the balloon expand? It was water vapor or steam. So it was water molecules. Please note, it's very, very important that we clarify this misconception that in this experiment, water was not decomposing. We were not breaking down the water into hydrogen and oxygen gas. Okay, this was not a chemical reaction. All we are doing in this experiment is a phase change. So we're having a look at a physical change. We're not looking at a chemical change. What did you hear inside the balloon when it started to cool down? Well, if you shook the balloon, it should have sounded like there was rain inside the balloon. So what caused that sound? Well, there should have been some water droplets inside the balloon. So where did the water droplets inside the balloon come from? Well, the water vapor condensed inside the balloon and it formed droplets of liquid water. So what happened to the balloon when it was cooled down in the cold water? Well, the balloon should have shrank back to its original size. And 8, what changes of state did the water undergo in this experiment? Well, we were having a look at evaporation and condensation. So there are just some terms that I would just like to clarify. And that is what happens when we are boiling water. So look carefully at this picture of boiling water at the top here. So here you can see the pot and you can see there are bubbles throughout the whole liquid. So I've got a question here for you, and that is, what do you think is inside each of these bubbles? So here's a close-up of the bubbles. What do you think is inside them? So let's have a look here. When a liquid boils, its particles move so fast that they break away from each other and they turn into a gas. Okay, so this is liquid water turning into water vapor. So these gas bubbles are water vapor. Now I need you to understand then, what then is evaporation? Okay, so evaporation is not the same as boiling, and we'll elaborate on this later on this lesson. Evaporation is only happening at the surface. So evaporation is only happening here at the surface of the container. and that is where the liquid is actually turning into the vapor. When a liquid boils, the particles become gas everywhere in the liquid. So here you can see the liquid boiling, and there are gas particles all throughout the liquid, not just on the surface. And this is why bubbles of gas appear throughout the liquid, and they are heated from the bottom and they rise up to the surface. So is there a difference between evaporation and boiling? Yes, there is, and this is possibly quite a commonly asked question in tests and exams. So please be sure that you understand what is and the processes that are going on, and write things down if you need to. So here we have two containers. So this container here is showing evaporation, and this container here is showing boiling. We are not going to be dealing too much in this lesson about vapor pressure and atmospheric pressure. We'll deal more with this to the end of matter and materials, but I will mention it now and we'll elaborate on it later. So for now, you just need to understand that with evaporation, the bubbles don't form. Okay, we just get a phase change at the surface. But with boiling, we actually get bubbles forming and they're rising to the surface. So evaporation is the process of turning from liquid into vapor, whereas boiling is the action of bringing a liquid to the temperature at which it bubbles and turns into vapor. So please notice there is a slight difference in the definitions here. So evaporation can take place at all temperatures. So just think of your washing hanging on the line to dry. It doesn't have to be a certain temperature before your washing dries. Whereas boiling occurs at a specific temperature. So for example, at sea level, water will boil at 100 degrees Celsius. So when a liquid is heated to its boiling point, bubbles form in the liquid. So here you can see the bubbles are forming in the liquid, and they rise up to the surface. And when that happens, we say that the liquid is now boiling. So if I just move out the way here. So this is a very nice answer summarized for the above question. Evaporation occurs only on the surface of the liquid, whereas boiling occurs throughout the entire liquid. So different liquids do boil at different temperatures. So for example, the boiling point of water is 100 degrees Celsius. The boiling point of alcohol is 79 degrees Celsius, whereas the boiling point of oxygen is minus 183 degrees Celsius. You'll deal more of this when you do chemistry in grade 11 and grade 12. I just added this in as a little bit of extra information, but for you to also understand that not every liquid boils at the same temperature. This is also a little bit extra for this lesson, and that is that liquids also boil at different temperatures depending on the different pressures. And like I said, we will do more of this towards the end of our section on matter and materials. So for example, if you are climbing Mount Everest or climbing a really high mountain where there's a huge change in altitude, water boils on Mount Everest at a temperature far less than 100 degrees Celsius. It boils at approximately 72 degrees Celsius. So that means you will never be able to have a hot cup of tea on Everest, because water boils, so it turns from a liquid into a gas while it is only still warm. So you can never raise the temperature of a liquid above its boiling point. So if you try to heat it more, it will simply just boil faster. You can never get the temperature of water above 100 degrees Celsius at sea level. So this little activity you will find on our worksheets at the end of this lesson for you to do. And I also think it is a great thinking task that helps improve your thinking. It's a compare-contrast Venn diagram where we look at the similarities and differences between boiling. So in the Venn diagram, where they cross over here, this will be, so this circle is for evaporation and this circle here is for boiling. Where they cross over here in the middle, this is how does evaporation overlap with boiling? So in what ways is evaporation and boiling similar? Then everything outside in this area is what aspects pertain to evaporation only. And everything in this area here is what aspects pertain to boiling only. So this is a really, really good task to do. If you don't want to do a Venn diagram, you can always tabulate the differences between evaporation and boiling. And I really recommend you do this activity because often you find this question in tests and exams. So just as a recap from previous lessons, and that is that water exists in 3 different states. So this is all the same compound. The compound we are looking at is H2O, which is made up of 2 hydrogen atoms and 1 oxygen atom. So this is 1 molecule of water. So this is 3 molecules of water and how they would exist in a gas. Here are water molecules and how the particle arrangement would be in a liquid, in a solid, and here are particle arrangements and what they would look like in a liquid. So please remember that there are forces of attraction and repulsion between the particles. So there are forces of attraction and repulsion between these particles, and forces of attraction and repulsion between these particles, and forces of attraction and repulsion between these particles. So each state of matter behaves differently, and the particles in each stage behave differently. So, heat is a form of energy. And when we heat a substance, we give the particles more energy and they are going to move faster. So we are going to say that they have a high kinetic energy. Temperature is a measure of the kinetic energy of particles. So heat can also be used to change the phase of matter. So it can change a solid to a liquid and a liquid to a gas. But we can also remove heat to change a gas into a liquid and a liquid into a solid. So the one thing that I need you to remember as we progress through the lesson is that a phase change always involves 2 things. 1, we're going to change the arrangement of particles, and 2, the particles are either going to absorb or release energy. So if we have a look here, these are just particles vibrating in a substance. Here if the substance is cold, and here if the substance is being heated. So this model also helps us to understand what happens to the particles when matter changes from one state to another. So from the previous slides, you can recognize here are water molecules as a gas, here are water molecules as a liquid, and here are water molecules as a solid. So we have water vapor, water, and ice. And if we want to go from a solid to a liquid, we need to add energy. And if we want to go from a liquid to a gas, we need to add energy. So as we go this way, we are adding energy. If we want to go from a gas to a liquid, or from a liquid to a solid, we need to remove energy. So these are some definitions that you can copy down. So they just help with each of the terms that we're going to cover this lesson. So I don't need to read through each of it with you. You can just pause the screen and copy down each of the definitions. Again, I'm sure you will get asked them in tests and exams. So if we have a look at this diagram here, how can we link these pictures up with what's happening in the picture here? So if we want to go from a solid to a liquid, we call that melting. If we want to go from a liquid to a gas, we call it boiling or evaporation. If we want to go from a gas to a liquid, it's condensation. If we want to go from a liquid to a solid, it is freezing. Now we're going to learn another concept today, and that is what happens if we skip a phase. So what happens if we go from a solid to a gas? So for example, with the dry ice here, that is a solid going directly into a gas. There is no liquid in this scenario here, and we call that process sublimation. Or the mothballs that you put out, they've got a very strong smell that chases moths away. Those mothballs go directly, they don't turn into a liquid and then a gas. The smell of those mothballs goes directly from a solid to a gas. So we call that sublimation. If we have a look at beautiful snowflakes here, that is going from that those snowflakes are being created by a gas, which is water vapor, going directly into a solid, which is the icicles, and we call that deposition. So under special circumstances, a solid can change directly into a gas without melting first. This process is known as sublimation, and its reverse, when a gas changes directly into a solid without condensing first, is called deposition. So here are a few questions for you to answer, just to check your understanding. So I've put the diagram in at the bottom for you to refer to. So what is the name of the process when a solid turns to a liquid? What is the reverse process to melting? What can we do to make ice melt quickly? Explain the steps that a solid must go through to become a gas. When we heat something, are we adding energy to it or are we taking energy away? And how do you think the particles in a substance behave when we give them more energy? So to help you answer those questions, when a solid is heated, the vibrating particles are given more energy. Their vibrations will become more and more vigorous until the solid particles are able to shake themselves loose from their fixed positions. The forces between the particles are no longer able to hold them together tightly, and the solid melts. So here you can see the particles are vibrating in their fixed positions. We are adding more energy, so the particles shake themselves loose from their fixed position. So here the particles are not held together as tightly anymore, and the solid melts. So when a liquid is heated, the particles are given more energy, so the vibrations become more and more vigorous until the liquid particles are able to shake themselves loose from their fixed positions. So the forces between these particles are no longer able to hold them tightly together, and these particles now whiz around faster and faster as they heat up. So soon some of the particles near the surface will have enough energy to escape out of the liquid. And once the particles are free from the forces that hold them together in the liquid state, they enter the gaseous state. Evaporation requires energy in order to break up intermolecular forces and excite water molecules. The higher the temperature of the liquid, the faster it will evaporate. So when the temperature of a gas is lowered, so now we're sitting with the gas and we are lowering the temperature, so we are removing the energy. The movement of the gas particles slow down as the energy decreases. So they will start to experience attractive forces, so it will cause these particles to move closer together and closer to each other, and eventually they will return to their liquid state. And in the same way as gas particles that are cooled down condense together, they form water droplets. And that process is known as condensation. So when a gas changes to a liquid, the state change is called condensation. So condensation is the opposite of evaporation. So by cooling the liquid, we would be removing energy from it. As the liquid particles lose energy, their movement slows down more and more. And as their movements become slower and slower, the attractive forces between them become stronger, and the particles will eventually lock into a fixed position in the solid state. So they're no longer able to move freely, but they are able to vibrate in their fixed positions. So now we say that the liquid has solidified. So by cooling the liquid, we would be removing energy from it. And as the liquid particles lose energy, their movement slows down even more. And as their movements become slower and slower, the attractive forces become stronger and stronger. The particles eventually lock into position in the solid state. They can no longer move freely and are only able to vibrate in their fixed positions, and we say that the liquid has solidified. So we are able to represent this phase change in a diagram. So on the vertical axis, we have temperature measured in degrees Celsius, and on the horizontal axis, we can have time in minutes, or sometimes you could find energy changes. So if we have a look at it, here we have our solid, and our solid is warming up. Then it plateaus out, that is while our solid is melting. And then as we heat it up even more, it becomes a liquid. Then our temperature gets higher and higher and higher, and the liquid then starts to boil. And if we take our temperature higher and higher and higher, after boiling, we get the gas phase. So this is just learning to take the particle model of matter and phase changes and put it into a graph. So I want to see, are you able to take this diagram over here that shows the changes of states and work out where would we put a gas, where would we put the liquid, where would we put the solid, where is the melting point, where is the boiling point, where does melting happen, where does evaporation happen, where does condensation happen, where does freezing happen. So pause the video if you have to and just spend time seeing if you are able to put the change of states onto this graph. So hopefully you were able to do it and you got something along this line. So I just want to show you again that on the vertical axis we put temperature. So in both graphs we have temperature. This is specifically a phase change graph for water. Different liquids, different substances are going to have different phase change graphs because different substances, like I mentioned earlier on, different liquids will boil and freeze at different temperatures. So this is just particularly for water. So we have temperature on the vertical axis. And then on the horizontal axis, depending on the interpretation, you can either put time or you can put heat absorbed. So you just, when you get this graph in a test or exam, please just look really, really carefully at the labeling of it and read the question carefully when you have to interpret the data. So in this line here, anything below 0 degrees, water exists as a solid. Water is ice. So from 0 degrees down, we have a solid. But what starts happening as we go over 0 degrees is we start to get a phase change. And that phase change is going from a solid to a liquid. So if we have a look here, we are melting. And our melting or freezing point is 0 degrees Celsius for water. Then if we start to increase our temperature above 0 degrees, so we start to add more energy and more energy and more energy, our substance, our water, is going to remain as a liquid. Then if we carry on heating the substance and we get to 100 degrees Celsius, particularly if we are at sea level here, we get another phase change happening. And that is our boiling point. So for water, we know that the boiling point is 100 degrees Celsius. So if we are moving from a liquid into a gas, we are going to get evaporation. Now, what happens if we are changing the temperature, but we're decreasing the temperature? So we are starting off with vapor, water vapor, and what we're going to do is we are going to cool that water vapor. So as we cool that water vapor, we are going to get condensation happening, and that's where we see little droplets of liquid forming. And then we get liquid droplets, and as we cool that even more and more and more down to, so we're cooling it down to 0 degrees Celsius, what's going to happen to that liquid at 0 degrees Celsius? It's going to freeze. And then if we take it below 0 degrees Celsius, we are going to find that we have a solid. So I know this diagram is a little bit tricky to understand. There is some exercises in the worksheets for you to practice going through. And again, if you are struggling, please don't hesitate to email us. So here's a little bit of thinking before we end off the lesson. What would happen if you tried to make an ice rink using dry ice? Would you be able to skate? And can you justify your answer? So if any of you have had the opportunity to go ice skating on normal ice, you will notice that as the blade goes through the ice, we get a phase change where the ice solid, because of the pressure and the friction and the heat, this ice slowly melts into water. So the reason why this blade can go on the ice and the reason why you're able to move is because of the thin film of water that's created. We get a phase change happening here because as you are skating, because of the pressure and the temperature, we are changing from a solid to a liquid. But if we had an ice rink made up of dry ice, I don't think your skate blade would be able to move because the ice is not, the dry ice is going sublimating straight from a solid into a gas. It is skipping the melting liquid phase. So here's a little evaluation for the lesson. I want to see if you are able to answer these questions. Again, you will find the memo for this in the worksheet section that's associated with this lesson. So you can pause the screen now and see if you are able to answer these questions. So we have A, which is representing a phase, C represents a phase, and E represents a phase. Then what is at B? Is that the melting point or boiling point? D, is that the melting point or boiling point? So B and D are referring to phase changes. Then 8 and 9 is referring to the process. What is the process going from a solid to a liquid? 8, what is the name of the process going from a liquid to a solid? For 10 and 11, what is the name of the process going from a liquid to a gas? And 10, what is the name of the process going from a gas to a liquid? And then what would you say is happening at 7 to the heat energy? So if you are able to do this graph, it means that you really have a good understanding of phase changes. So the overview of the lesson is that you should now be able to use the particle model of matter to explain temperature and energy changes. You should understand that how materials can change their states and how particles and phases melt and evaporate and condense and freeze. You should be able to draw phase diagrams with increasing temperature and you should be able to understand graphs and how we use them to illustrate the phase change of a substance. So here's our think link. Were you able to spot all these pictures throughout the lesson? Hopefully you were, and hopefully you are able to explain what is happening in each of these pictures and link it all up with the particle model of matter and phase changes. So thank you for today's lesson. I think what a really cool summary would be is if you could draw a little sketch graph like this and see if you're able to explain what is happening at points 1, 2, 3, 4, 5, and then take it further. See if you can annotate this phase change graph as much as you can, and then also see if you are able to do this little phase change concept map. If you do that, that means you would have summarized the particle model of matter, and you will all be ready to go and write your first test. If you do have any questions of today's lesson, please email grade8@worksheetcloud.com. And to end off with a little cartoon, it's about a hipster ice cube, and he says, "I was water before it got cool." Thanks for joining us today, grade 8s. I really loved having you with me. I know I am missing the pupils that I teach so much, so I'm so glad you could join me today. And this lesson was brought to you by WorksheetCloud. I look forward to seeing you for our lessons later on this week. Goodbye.